All right. Well, let's take a look at where we're going to be today in 5.4. In 5.4, we're going to begin to add to several more tests that we can actually try to use when coming across a particular series. So in this section, we're going to talk about the comparison and the limit comparison tests. So over here on the list, I would kind of be adding those on this side. So I would have, again, comparison test and limit comparison test. Okay, so again, adding some more tests to the lists. All right, so let's take a look at how exactly I might use these tests and what exactly they're good for. All right, so if I take a look back at this opening motivation, here's what we got. How could we show that this series is going to be convergent? Now, there's a couple things I might note about this series immediately. First off, I'd love to go through all of my different types of series. This doesn't seem to be telescoping. It doesn't seem to be like a p-series like we talked about last time, because I kind of have this value of n in the exponent. Oh, but that might lead me to believe that maybe it's geometric. But the only issue is this kind of +1 that's down here. That's a little bit annoying. If that +1 wasn't there, this seems like it would be perfectly geometric. I could maybe rewrite this in a particular way to get it there. But that +1 seems to be causing a problem at the moment. And very obviously, this is also not the harmonic series. So none of my types of series are going to work well. If I went through a lot of my other tests, I could also see that while I might be able to do something like an integral test, I don't really want to integrate the matching function for this. And I don't really think that test for divergence is going to get us anything other than 0, which means it's inconclusive. So we're going to go ahead and take a slightly different approach. So I'm going to go ahead and state this. I'm going to note that, again, this series formula there that I have on the inside is very, very similar to something like a geometric series, if only that +1 wasn't there. Now notice that I'm going to be comparing these two fractions, one with the +1 and one without. The one with the +1 certainly has a larger denominator for all possible values of n, which makes its fraction overall smaller, again, for all values of n greater than or equal to 1. But I can also add to this and say that more than that, this particular series associated with that formula is indeed a nice geometric series. You could see that I could go ahead and rewrite this as a 1/2 all to the power n. I could then rewrite that as a 1/2 times a 1/2 to the n minus 1. And if we were to check to see if that series converges, it definitely does converge. My value of r, absolute value, is less than 1. And if you could double check to see that it actually does converge to precisely the value of 1, using that a over 1 minus r formula we mentioned before. So this is kind of an interesting set of things that I could go ahead and note. But what is it good for? Because while I know that this series might converge, this series is something totally different. Okay, but here's what I have. I can say that these facts imply that if, let's make S sub k, again, this is a green S sub k, so it's going to stand for some partial sums. I'm going to use the value of k here since n is already in use, but it'll have the same meaning. I'm going to add from the series all the way up to k things, and this will be from our original series, sum of the first k things. And how about we let t sub k, again, I'm going to use a different variable because I already used s, and n is already in play. How about this stands for the sum of the first k things out of our new series, which again, we said already converged to 1. Okay, so if I have these two particular guys, then it seems like I could easily state the following. These addition problems are finite, and all the terms in this left addition problem, we said, are smaller than the terms that are over here. So the S summation is a sum of a bunch of small things, and the T summation is a sum of a bunch of big things. And so it doesn't seem kind of strange to maybe argue the following, that S sub k will always be smaller than T sub k, and we know that T sub k is definitely always less than or equal to 1. We know it converges to 1, and so since it starts with values like 1/2 plus a quarter plus an eighth, it's working its way up to the value of 1, but it's beneath it. And I could state this is true for all values of k greater than or equal to 1. Seems to be this kind of hierarchy that are forming. But now notice that I can make some really interesting claims about the S sub k. I can say this means that S sub k is bounded above by 1, right? Like there's no way that S sub k can get bigger than the number 1, since T sub k never gets bigger than it, and S sub k is less than T sub k. But I could also maybe note the following. I'll say here, also, S sub k is increasing. That is, every time I add or increase the value of k by 1, I've added something else into the addition problem, and that running total is getting larger. And notice I'm only adding positive things here, so there's no chance of like adding a negative so the result goes down. I'm only going to have the result get larger. So what I can look at here is that I have a sequence, S sub k, that is both bounded above and increasing. But then I can think about what that means. Take a moment to think back about what we talked about with sequences in our first two sections, 5.11, 5.12. If I know that a sequence is bounded above and it is also increasing, what else do I know about it? Well, you might be able to see that I know the following. I could say, by the monotone sequence theorem, abbreviated MST, we know that S sub k must converge. We don't know what it converges to. Remember, MST never told us that, but we do know that it converges. But if S sub k converges, then what do we know about the original series? Well, then by definition, that series must converge. So by definition, this series must converge. Boom. So this is a really powerful argument. What we can see here is that it relied on this opening comparison and a couple other things in order to be able to arrive at this conclusion. Now we're going to summarize all of this down below in what we call the comparison test. And you'll see a lot of these same elements just kind of abbreviated. So our arguments that we write will be able to be a bit simpler. Here's what we have. Suppose that I have a series with A sub n and a series with B sub n. And these are series with non-negative terms. We saw up above that we had series with non-negative terms. No negative numbers ever occurred in the addition problems above. And that was important when we wanted to argue that like S sub k was increasing. If I ever added on something negative to the running total, that running total would go down. And so I wouldn't have increasing. So I need to make sure I have a series with non-negative terms. Negatives are bad, zeros and positives are okay. Well, once I have that, then I can reach one of two conclusions. We'll say this. Let's suppose that the series with the B sub n is convergent, and A sub n is less than or equal to B sub n. So again, that means the numbers in the first addition problem are always the same size or smaller than the numbers in the next. And if the numbers in that big addition problem end up being convergent, then it seems reasonable to say, as we saw up above, that the smaller addition problem would be convergent. And the argument that we had up above kind of shows why, because we can get the partial sums of that smaller thing to be bounded and increasing and converging. Okay? In a very, very similar way, we could actually argue that if, let's say, A sub n was divergent, again, A sub n still the smaller set of numbers, smaller list of numbers, then again, by a similar argument to what we did above, we could claim that the series with B sub n is divergent. So this will actually be extremely similar to the idea of the comparison theorem that we had with improper integrals. If the small thing is diverging, so is the big thing. And if the big thing is converging, so is the small thing. Okay. Of course, we had a couple notes down here. When we say for all n up above, this can technically be adjusted. It might be that for all n past a certain point, this is true, and we can just adjust slightly. And we'll see kind of how to do that in the next example. Okay, I'm going to go ahead and break the video here, and we'll pick up with the examples in the next video.